in the physical process. But 6-2 is another matter. 6-2 has unknotting number 1. And if you switch the crossing in the middle there, you get an unknot. And so that can be accomplished with 2 reconnections. And so 6-2 can be undone with 2 reconnections. It just didn't happen in the physical model that we were looking at. Here's a picture of 6-2 happening that way. If we took the middle crossing and had a little curl near it, and then started there, we could undergo by going through a reconnection, pulling that back and pushing it back over the top and reconnecting again, and we have an unknot. So you can imagine that something like that might happen physically, but it certainly required some special conditions for it to pull back and come back over. And I don't know what those conditions would be. So we do need to go back to those differential equations models and try them again in the light of these remarks. We haven't done that. So we've seen that a physical sequence of reconnections takes 6-2 to the unknot, as I said. But we want some lower bounds for the number of needed reconnections for a knotted vortex. So I'm going to let R of K be the least number of reconnections needed to transform a knot to a collection of unknotted circles. And you can get some lower bounds easily with the classical signature of a knot. I'll explain in a moment, but the signature of the trefoil is -2, and the signature of 6-2 is -2. Those absolute values true. Those mean something in this regard of having 2 reconnections needed. What's the situation? Situation is this. We know from Murasugi's work long ago that the signature of the knot is less than or equal to 2 times the 4-ball genus, the least genus of a surface bounding the knot in the 4-ball. So if you believe Murasugi's theorem, we know that the genus, twice the genus is less than or equal to the reconnection number. That's what we remarked before. Every hole could be at least 2 reconnections. So therefore, the signature is less than twice the genus is less than or equal to the reconnection number. So the absolute value of the signature of the knot is a lower bound on the reconnection number. There's an easy classical one. I won't remind you about the definition of the signature, but I am reminding you by flashing the slide. I just won't talk about it. But I do want to talk about surfaces that bound a knot and how these are related to the classical ciphered surface of the knot. So here's a knot, and if I do oriented smoothings, not re-smoothings, but replacing the crossing by a smoothing in an oriented way at every crossing. And then I bound each of the resulting circles, ciphered circuits, with a disk, and then add back in little twists for each of the crossings. I obtain an orientable surface whose boundary is the knot. This is the classical ciphered surface. And I want to use that in thinking about surfaces that might arise in the reconnection process. In order to do that, I'm going to think about the ciphered surface in a slightly different way. What I'm going to do is I'm going to, at every crossing, I'm going to go through a reconnection at that crossing. Let me point. Right here, you see I have oppositely oriented edges, and I can go through a reconnection there, and I'll go through a reconnection here, and I'll go through a reconnection here. And as you see, the result of that will give me a set of circles. And those are just exactly the same as the ciphered circles, except that we're preserving a little bit of writhe. And these circles, so you see that we could bound them with disks into the 4-ball. So that means that we can construct the ciphered surface as a surface bounding the knot into the 4-ball by going through one reconnection at each crossing and then bounding off the resulting circles into the four-ball. And we obtain a surface in the four-ball whose genus is exactly the same as the genus of the ciphered surface. And in fact, this surface that I have described for you into the four-ball is the result of taking the ciphered surface in three space and gently pushing it into the four-ball, keeping the boundary in three space. But I've described it by reconnection this way. So that means that we have an upper bound on the reconnection number. The upper bound on the reconnection number is going to be related to the number of reconnections you need to make from your ciphered surface in order to get to an unknot. So the most trivial way to do it is to just go ahead and do it at every crossing, but that isn't necessarily the most efficient way. So for example, in the case of the trefoil, we can get to an unlink in 3, but we didn't need to get to an unlink in 3. We could have just done 2 of these. So you see, there is this relationship with the ciphered surface. Let's go back to the slideshow. So if I have a classical knot diagram and it has C of K crossings and S of K ciphered circles, then the genus of the ciphered surface is given by 1/2 of C of K minus S of K plus 1, I claim. And I leave it to you to prove that by yourself by checking it with the Euler formula. The Euler formula says that 2 minus 2g is equal to vertices minus edges plus faces for a decomposition of the surface. And you have a decomposition of the surface coming from the way I described the ciphered surface, and you make the counts correctly, and you'll see that that's what happens for a knot. And for a link, I have to add a term involving the number of components. So twice the ciphered genus is the number of crossings minus the number of ciphered circles plus 1. We'll come back to that. So we have the following, that if I have the four-ball genus for a link, and I consider the reconnection number for that link, then twice the four-ball genus is less than or equal to the reconnection number. And in the case of signature for link, I can augment what I said before and count the number of components as well. We'll see how that works. And we have then the following theorem, that if K is a positive link, this is the most general theorem I can make at the moment. If K is a positive link, then the four-ball genus of K is equal to the ciphered genus for any positive diagram of the link K. And so if K has a positive diagram, then the reconnection number is going to be greater than or equal to twice the four-ball genus, which is C of K minus S of K plus 1. And in fact, we're going to see that it's equal to it. And we know this by Rasmussen's invariant. Rasmussen's invariant and a couple of papers past the one that Rasmussen wrote tell you this about the least genus in the four-ball that's given by the ciphered genus. So we can apply that here. So I claim that if I have a positive link, then the reconnection number is exactly given by this count. And we'll see by doing some examples how that looks. You take the number of crossings minus the number of ciphered circles and add 1, and you have the genus that you want. You have the reconnection number that you want. So we already know that the reconnection number is greater than or equal to that number from Rasmussen. And it suffices to give a sequence of exactly this many reconnections that will undo it. And we also know that we can just use every crossing. So C of K will suffice. But I'll show you some examples to see what I'm saying, but I'll read it. If we look at the ciphered circles, then we can locate S minus 1 sites of these that, if connected, will produce an unknot. And then we don't have to perform connections at everybody. We just perform C of K minus S of K minus 1 kind of reconnections, and we're done. And that gives the answer. So you need to see an example in order to understand what I just said. Let me not use that example, but use this one. Here is a torus knot of type PQ. P equals 3 and Q equals 4 in this case. So we have four little braids of type 3 here. And you'll notice that the number of crossings in the PQ torus knot is P minus 1 times Q, because each of the little braids has P minus 1 crossings in it, and there are Q of those braids. So the number of crossings is P minus 1 times Q. And the number of ciphered circles is P, because as you see below, when you smooth all those crossings, you get exactly 3 circles in this 3 case, and P in general. All right. So I'm just doing the calculation to show you how this works out. So twice the ciphered genus of K is the C of K minus S of K plus 1. C of K is PQ minus Q. S of K is minus P and plus 1. And that is equal to P minus 1 times Q minus 1. So that tells us that the reconnection number for the PQ torus knot is P minus 1 times Q minus 1. And of course, Rasmussen proves that the 4-ball genus is equal to P minus 1 times Q minus 1 over 2. So these results are dovetailing into one another. But what did I say about knowing how to reconnect? Well, I've done an example here that shows you what I mean. Here's an arbitrary positive knot, some positive knot. And I have smoothed all the crossings in the ciphered form over here. That's the same as doing doing reconnections at all of them, but I have smoothed all of them. All right, I have done that, and now you see a collection of ciphered circles. I think I wish to point again. So here's the collection of ciphered circles, but we don't want to do reconnection at every crossing. So what we're going to do is we're going to leave this one connected to that one, this one connected to that one, and this one connected to that one. We can find a chain of ciphered circles, each connected to the other, and leave the chain alone. Leaving the chain alone, but smoothing everyone else gives you an unknot. So by doing exactly the reconnections in the complement of the chain is checkmarked. We're doing the reconnections in the complement of the chain, we end up with this fellow here, an unknot. And therefore, the reconnection number is exactly equal to C of K minus S of K plus 1. So I can always reconnect it to an unknot by using C of K minus S of K plus 1 reconnections. And that is greater than or equal to the reconnection number, as we already knew. And therefore, the reconnection number of this positive knot is exactly 7 in this case. And the same argument applies to the torus knot. You see, in the case of the torus knot, we could have left these two alone, and then we would have done 1, 2, 3, 4, 5, 6 reconnections, and 2 times 3 is 6, and that's the answer in this case. So you see how it works. Oh, I'm sorry, I made the wrong choice there. I wanted to go back to my slideshow. Okay, so I think these examples illustrate exactly what's going on for you. Rasmussen tells us that that's a lower bound, and geometric construction using the idea of the cobordism ciphered surface shows us that it in fact is equal. And so we know the reconnection numbers for all of these knots, all positive knots. And this opens the book again on doing experiments with these, because I'm sure that if we do experiments using the Gross-Piatowski differential equation, we'll find that in many cases, the reconnection number will be much larger than this, and in some cases it will be equal to it. Be very interesting to see how it relates to the known reconnection number for these knots, and there's a nice infinite class of them. Here's a nice example for a link, a simple example. If we analyze the link, over here on the left, I've produced its ciphered circles, and we see that the number of crossings is 4, and the number of ciphered circles is 3, and C minus S plus 1 is 4 minus 3 plus 1 is 2. So this will reconnect in 2, and how do you see that? Let me again go so I can point. How do I do it? Well, I'm going to look at the, I'm going to reconnect here and reconnect here and not reconnect there or there. And the result is that the 3 ciphered circles are connected in a chain. This one up here, sorry, connected in a chain here, and that's all I needed. I needed, I'm sorry, they're connected in a chain here and up here, right? And then we did the resmoothings, the reconnections on the other 2 crossings, and it gives us an unknot. So this went down to an unknot in 2, but it might, if you chose the wrong reconnection, get you a higher number. And I would expect that in an experiment, this would easily happen. So for example, if the reconnection happened along the middle circuit here, like that, we would end up with 2 hop links. And assuming that it didn't go backward, the hop links would each require a reconnection of their own in order to become undone. And so we would get to unknotted things in 3 rather than 2 if we did it in the wrong way. So as you see, there are a lot of experiments, and one can think of cascades of reconnections and the various reconnection numbers that will come out of the cascades in doing this sort of thing. Oh, I'm sorry, I keep choosing the wrong guy there. All right, let's go back to the slideshow. There. Okay, so that's the main result. It would be interesting in this talk if I had to review how Rasmussen's theorem works, but that's a little beyond doing it in this talk, so we won't. But I would like to know what happens in experiments now very much. I want to show you something else about topology change. Go back to movies for a moment, and then maybe we are stopping a little early on this talk. Okay. I'm going to show you that this can happen in a real life situation. You have a line vortex, and it has a little curl in it, and the curl does slip under an edge, and then a reconnection occurs at the crossing. It's just like what I was telling you about. It really does happen, and you get a link. So you increase the complexity of the topology instead of decreasing it. And you might wonder, how could that happen? But it does happen, and it happens in an experiment beautifully done by Alexienko in Novosibirsk. And you probably couldn't see that very well, but I'm going to show it to you more slowly. Here is the loop. Oh, and I should explain that Professor Alexienko's experiment involves a turbine. So it's simpler than the Irvine experiment, but it isn't a closed loop vortex. It's a turbine, water rotating in a long tube, which is wider at the bottom than it is at the top. And the wider at the bottom than it is at the top allows some things to float upward. And that's what happened here. You can see the width getting larger as it goes down. And you can see that something funny happened there, but hard to tell. So let's look at what happened. This loop is floating upward. And it floats upward underneath the other part of the vortex and keeps on moving upward a little bit, and it's starting to get close to another one. Notice, by the way, the orientation. If you put an orientation down on this and then walked along it, you'd be coming back up here. So these are oppositely oriented. They can interact, and they do interact. They start getting closer, and they interact. And I have no film, I have no pictures of the interaction from here to the reconnection. I have this shot, and the reconnection has happened. That's it, just like that. And now you see, because this lasso was going around the other one, when this reconnects, you end up with a link. So in the context of Professor Alexienko's experiment, it is possible to have a bit of line slip underneath a bit of line and reconnect, like we were seeing in the crossing switch. And for the topology, in fact, to become more complicated. So it's not impossible that some of the topologists' ideas that are in here may happen in reality. And this is what we just saw. So I thank you, but I think in the light of the fact that we have a couple more minutes, I would like to show you a little more phenomenology. Oops. I want to show you a little more phenomenology. This is another movie from Alexienko's lab, but well, let's run it at normal speed. Now there you see a movie of the actuality of the reconnection. I'm just wanting to center that a little bit for you. So they're coming together, they're near one another, they're getting very close, they interact. And then the interaction is obviously quite complex. And you see that there's microstructure going on here. You see those filaments coming. So you end up with these filaments of vortexing going on in between the larger parts, which are stabilizing and forming the reconnected vortex. And the filament remains for a while in between them as they float away. So it would be very interesting to understand better the details, the actual physical details of this. Let me see if I have another one that I would like to show you. Right. In this case, what did you see? You saw the vortex getting near to itself. You saw two edges of the vortex getting near to one another, and filaments happening between them. Quite an intensity of interaction, but there was enough momentum on the larger vortex so that it didn't reconnect, it just passed by. So it looks like a Feynman diagram for the physical interaction between two things involving an interchange of particles, right? Only all this is a macroscopic level thing, not quantum. And very interesting fluid dynamics going on that one would like to understand how to model it, or how to model it with some simplification so that one could think about extra topological things that are going on here. So for the topologists, you think of, well, there will be tubes between them, and how many tubes will there be, and many questions that you can ask. So I thought I would share that with you. because it is really quite remarkable. And so what have we done today? We've talked about some physical vortices. We've talked about the Kelvin theory. We've talked about how one can actually find the reconnection number, the least number of reconnections needed to unknot a knot for positive knots, which includes Taurus knots, and that there's a simple formula for that involving the Ciphered circles, and that the phenomena of reconnection is really quite a fascinating physical phenomenon that, with these remarks, is related to some of our favorite topological invariants. So I'll stop there.
Thank you very much for your nice talk. There is a question or comment? Okay, so one question is your reconnection is oriented, cobordism is an oriented surface. Yeah, it's no oriented case. There is no oriented surface.
I'm not sure I understood the question.
Yeah, it's reconnection is a cobordism of knot. Cobordism surface.
What I'm saying is, I'm saying the following. That two knots are coordinate if there is an orientable surface in force space between them. Cobordisms can always be delineated by a sequence of isotopies, births, deaths, and reconnections, if you want to use the term reconnection, right? Saddle point moves.
Okay.
So we can ask of a of two knots, what is the least number of reconnections in a cobordism between them?
Yeah.
Right? And that would be a reconnection number for a pair of knots. And I'm defining the reconnection number of a given knot as the least number of saddle points in a surface that bounds the knot. And that's the same as the least number of, for a knot, it's the same as the least number of holes. It's the same as the genus. So if you know the genus in the foreball of the knot, you basically know the reconnection number.
Okay, thank you.
In the case of a link, there are some further reconnections that can happen in terms of link components melding with one another.
Okay, thank you very much. There's other question or comment?
Excuse me, may I ask you a question?
Yeah, please.
First, thank you for interesting talk. I have one question. As I understood, in this case, we are considering the situation in R3 and
the situation in
R3, usual R3.
Oh yeah, in R3 certainly, yes.
Then, of course, as I know, the similar work can be done for the roughly speaking virtual knots in the surface, not in R3, but the second surface.
Yes, certainly. For example, I can make the same theorem, exactly the same theorem, for positive virtual knots. A positive virtual link has the reconnection number with exactly the same conclusion because of the work that we did with, because of work that I did with Heather Dye and Aaron Kastner using Covanov homology and a Rasmussen invariant for virtual knots. So the same conclusions. You get exactly the same conclusions for a reconnection number for virtual knots. But there you're thinking of everything as stabilized. Right.
Yes,
You don't care about the number of handles in the surface if you can get rid of them. It's virtual knot theory. If you wanted to ask the further question of the knot is actually in a specific genus thickened surface, and yes, the same question, then we could probably do some work there too, but we'd have to use a version of Cavana homology for that's a little more special to the surface.
Okay, thank you. Then another question is then, is there corresponding how to say situation in physics for the knots in the second surface or other 3 manifolds?
Good question. I meant to mention it. I don't know. I don't know whether there's an interest in having vortices restricted to being in a thickened surface, but it might be possible to do computer experiments with them, though.
I see. Thank you very much. Thank you.
There is another question. Okay, so thank you very much. Nice talk.
Thank you.
Next talk will begin with 1100. Just rest.
So the next talk will be in 30 minutes or so, right?
In 15 minutes, yes?
Yes, in 15 minutes, right?
Yeah. Okay.
Okay, so let's start. The next speaker is Professor Young Chen from Beijing Normal University. The title is on region crossing change. Please start.
Okay, thank you. Can you hear me?
Yes.
Okay, good.
Okay, please start.
First, I would like to thank the organizer for giving me an opportunity to give a talk here. And today, I would like to discuss some recent progress on region crossing change. Actually, which was originally partially proposed by Professor Carl himself. Okay, I would like to begin my talk with a question. First, I would like to discuss the notion of a hypergraph. By a hypergraph, we mean it consists of two sets, the vertex set and the edge set. In my talk, all hypergraphs are assumed to be finite. So the vertex set consists of some finite vertices, and the hyperedge set consists of finitely many hyperedges. For a hypergraph, a hyperedge is just a subset of the vertex set. So for a Euler graph, an hyperedge, maybe I should say an edge consists of two elements, because an edge has two endpoints. But in a hypergraph, it could be an empty site or just 1, 2, 3, 4, 5. So here we have a very simple example. Here we have three vertices, V1, V2, V3, and here we have three hyperedges. The first one, E1, is just the V1, and the second one is V1 and V2, and the third one contains all the vertices. So with a given hypergraph, we can define an incidence matrix, which is if we have n many vertices and m many hyperedges, then the incidence matrix is a m cross n matrix, and the entry Aij is equal to 1 if the vertex Vj belongs to the hyperedge Ei, otherwise it is 0. So for example, just for this hypergraph, it's easy to find that the incidence matrix has this form. So each row vector corresponds to a hyperedge. So this is E1, E2, and E3. So each column corresponds to a vertex V1, V2, V3. So now you have 3 cross 3 matrix here. I would like to remark that usually the incidence matrix is defined to be the transpose of this matrix, but since we just concerned with the rank of this matrix, so this is not a big deal. So by a state of a hypergraph, we mean a function from the vertex set to the set of two elements. Maybe we can regard it as Z2. So in other words, a state is just an assignment which assigns a 0 or 1 to each vertex. And also we can view a state as a row vector. And we say two states are equivalent if the difference between them can be written as the linear combination of some hyperedges. So here we just regard the state and the hyper edge is our low vector. So if you can find some coefficient, and each coefficient AI is belong to is just a 0 or 1. If you can find such a linear combination, then we say these two states are equivalent. So the question is, how many non-equivalent states does H have? Actually, the answer to this question is quite easy, because you can find that if there is no hyper edge, then we have 2 to the power of n different states. If we have one hyper edge, then we have one relation. So the number of the non-equivalent states will be divided by 2. And by repeating this, you can find that the answer to the question is this. So in order to answer the question, you just need to calculate the rank of the incidence matrix. For example, for this very simple hypergraph, we can find that the rank of the incidence matrix is 3. So it follows that all the states of H are equivalent. So what does it mean? Oh, sorry. Sorry. So recall that H contains 3 vertices. Maybe we can say V1, V2, V3. And each of them, by state, each of them is assigned with 0 or 1. For example, we can choose, for example, maybe just 0, 1, 1. So after that, you can use the, maybe I should, sorry, I choose this is V1 and this is V2, this is V3. So we can use the first hyper edge E1 to transfer this state to another new state, which is 0, 1, 0. And next we can use sorry. Let me assume this is V1, this is V2, this is V3. So we can use E2 to get a new state 1, 1, 1. So all the states of H are equivalent, means that you can use the hyper edge to connect all the states. For the rest of my talk, I will show you some examples, and the solution of these examples can be translated into the question of calculation of the rank of the incidence matrix of some hypergraphs. Let us begin with a very trivial game, game 1. Game 1 means that in the incidence matrix, 1 appears just once in each column. So in this case, it is evident that all the non-zero low vectors are linearly independent. So in this very simple case, it follows that if there exists no empty hyper edge, then the rank of this matrix is nothing but the number of the low vectors. So in this case, the number of non-equivalent states is equal to 2 to the power of n minus m. And all the states are equivalent if and only if m is equal to n. So this is actually a very trivial case, but I would like to choose it as the first game. So for the second game, I would like to discuss the case that 1 appears twice in each column of the incidence matrix. Actually, this game came from this question. Recall that a graph is we can choose a signed simple connected graph. Here, signed means that each edge is assigned a positive one or a minus one, and simple means that so there is no loop and multi-edge. Yes. Of course, the connected means just connected. So for a given signed graph, we can take an operation called the vertex switching. So vertex switching will reverse the signs of all the incident edges to the vertex. For example, for the first signed graph, if we take the vertex switching on this vertex, then this sign, this sign, this sign, and this sign will be switched. So we will get a new signed graph. And then we apply the vertex switching on this vertex. We will get the third signed graph. And finally, after taking vertex switching on this vertex, we will get a positive signed graph. So the question is, how many signed graphs are there over an unsigned graph up to vertex switching? We can translate this question into a language of a hypergraph. I mean, if we are given an unsigned graph G, then we can construct a hypergraph as follows. First, each edge of G corresponds to a vertex of H, and a vertex of G corresponds to a hyperedge of H. If Vi is incident with EI1 to EIS, then the corresponding hyperedge is nothing but this set Vi1 prime and the VIS prime. Then a signature, I mean a sign, is nothing but a function from the edge set to this set of two elements, and it can be written as a row vector. Actually, because this hypergraph, we just interchange the row of edge and vertexes, so it's easy to find that the incidence matrix MH is nothing but the usual incidence matrix of MG, and so they have the same rank. But the reason I write it in this way because I just want to use the language of a hypergraph. So the answer is, recall that our question is how many signed graphs are there over an unsigned graph up to vertex switching. So the answer is, first, the number of signed graphs is equal to this. Yeah. So in order to calculate the number of signed graphs, it is sufficient to calculate the rank of the incidence matrix. And it was proved by Nasra, Lulavo, and Spina in 2015. The rank of a connected graph is equal to, actually is one less than the number of vertices. Actually, the proof is quite easy. For example, if we have a connected graph, just like this. So it means that it is easy to find that. Notice that now in this case, each vertex corresponds to a row vector, and the sum of all the vertices is equal to 0. I recall that we are working over the coefficient Z2 because each edge has two endpoints. So these two endpoints will have two contribution to this edge. So 1 + 1 is equal to 0. Modulo 2. So it means that the sum of all the vertices is equal to 0. And the key point here is this is the only relation. So it follows that the rank of it is equal to the number of vertices minus 1. And it follows that if we want all signed graphs over a connected graph are equivalent, if and only if this graph is a tree, because just in this case, this is equal to 0. So another question is, when a signed graph is switching equivalent to a positive graph, just like in this example, we show that this signed graph is switching equivalent to a positive graph. So actually, this is a very classical result proved by Harari about 17 years ago. He proved that if G is a simple signed graph, then G is switching equivalent to a positive graph if and only if each cycle of it has a positive sign product. And equivalently, if and only if the vertices of G can be partitioned into two subsets. For example, this is one subset, and then this is another one. So we have some vertex here, we have some vertex here. And if an edge connects the vertex in different sets, then the sign of it must be negative. And this kind of edge will have the sign positive. So if and only if the graph G has this form, then it is switching equivalent to a positive graph. And this kind of signed graph are called balanced. Actually, in the theory of signed graph, the balanced graph are very important. So this is the second game because each edge has two endpoints. So in this case, 1 appears just 2 times in each column of the incidence matrix. Okay, so let's turn to the game 4. So maybe you would like to ask where is game 3? We will come back to game 3 later, but let us first talk about game 4. In game 4, 1 appears 4 times in each column of the incidence matrix. And in this example, this is a real game. Let me tell you a game called the Range Selected, which was proposed by Professor Kawauchi and Sumizu and Kishimoto about 10 years ago. So how to play this game? First, we assume that we are given a flat node diagram on a plane, just like this. And each crossing point is equipped with a light bulb. Yeah, so we have 3 light bulbs here, and some. So we can click a region to switch those light bulbs on the boundary of this region. And the aim of this game is to light up all the light bulbs. So, for example, if we are given a state like this, then we can click this region. Then by clicking this region, we just turn on this light bulb and turn off this light bulb. So we will get a new state like this. And we can then click this region. So we are down here and all the light bulbs are on now. So the question is, when can we achieve the goal? Is it true that for any node diagram and any state, we always can achieve the aim? Actually, the answer is yes. So first, I would like to talk about so-called the region crossing change, which was suggested by the title of my talk on the two-sphere. In 2010, Kishimoto proposed a new local operation called the region crossing change. So what is region crossing change? Region crossing change is a local operation on a node diagram or link diagram. So if we take a region crossing change on a region R, then we just switch all the crossing points on the boundary of this region. For example, if we take the region crossing change on this region, then this crossing point and this crossing point will be switched. So we will get a new neural diagram. So this is a right-handed trefoil, and this is a diagram which is a knot. Kishimoto asked the following question: is region crossing change an unknotting operation? For example, in this example, we can show that we can use region crossing change to unknot the right-handed trefoil. But we know that first is the trefoil has infinitely many diagrams. Can we always achieve our aim for any diagram of it? And how about other knots? So in order to answer this question, I would like to introduce a notion called the region crossing change admissible. So assume we have a link diagram D, and we choose some crossing points of it. We say they are region crossing change admissible if one can switch these crossing points and preserve all others by a sequence of region crossing changes. For example, these two crossing points are crossing change admissible because we can use this region to switch these two crossing points. Of course, these three crossing points are also region crossing change admissible because we can use this region to switch off them. The main result of Ayaka's Mizu is that she proved if we have a knot diagram and we choose any crossing point of it, then this crossing point is region crossing change admissible. So in other words, crossing change can be realized by region crossing change. So as a corollary, we know that crossing change is an unknotting operation. So it follows that region crossing change is also an unknotting operation for knots. So it means that actually this result does not depend on the choice of the neural diagrams. So for any diagram of a trefoil, you can always find some regions such that by taking region crossing changes on these regions, you will get a new diagram which represents the unknot. Okay. Here we have some remarks. If one have a unknotting operation, one can consider the corresponding unknotting number. It is very natural to define the unknotting number of region crossing change to be the minimum number of region cross change needed to unknot knot K among all the knot diagrams representing this knot. However, if we choose this definition, each non-trivial knot has a knotting number 1. Actually, this is an older result proved by Enda in 1992. And during the past 10 years, Ayaka's result has been extended to many other cases. For example, integral region crossing change, which replaced the coefficient Z2 to Z. And Katakami also studied the region crossing change on virtual neural diagrams. And later, Mizu also studied that the region crossing change is an unknotting operation for special graph diagrams and for the region Friesen crossing change, which means that by taking the region Friesen crossing change, you switch all the crossing points not on the boundary of this region, and the crossing point on the boundary of this region will be preserved. And this is also an unknotting operation. And she also showed that region crossing change is an unknotting operation for theta curves, something like this. Okay, so this is the result for knot diagrams and some generalized objects. A simple observation is that region crossing change is not an unknotting operation for links. For example, for the standard diagram of the half link, here we have 4 regions. Here R1, R2, R3, and R4. It's easy to show that whatever you do, you can just get this kind of diagram of half link, but you cannot get another diagram which is a trivial link with 2 components. Yeah. So the following question is, for which kind of link diagrams region crossing change is an unlocking operation? In order to answer this question, we can go back to construct a hypergraph. So for link diagram, and we use C1 to Cn to denote the crossing points and R1 to Rm to denote the regions. Here we always assume that this link diagram, we assume it is connected. Yeah. So now we can construct a hypergraph H such that each crossing point corresponds to a vertex of this hypergraph, and each region corresponds to a hyper edge, such that if we have some crossing points on the boundary of this region, then the corresponding hyper edge contains all the corresponding vertices. And now the answer is the number of non-equivalent link diagrams up to region crossing change is equal to 2 to the power of n minus the rank of the incidence matrix. So in order to answer this question, we are sufficient to calculate the rank of this matrix. This is an example. So if we consider a Bromine ring, and now we have 1, 2, 3, 4, 5, 6 crossing points, and we have 8 regions. So now we will get an incidence matrix like this. So for example, C, region C, it had on the boundary, we have crossing C1, C2, and C5. So you will have a row vector such that the first place, the second place, and the fifth place are 1. And here we have 3 zeros. Because we assume that the link diagram is connected, it is easy to find that the number of regions is 2 more than the number of crossing points. So this matrix has the form of C plus 2 cross C. And now we can restate Ayaka's result as if D is a node diagram, then the rank of this matrix is equal to C. For example, if you have, so it means that the rank is nothing but the number of crossing points. Of course, this is correct for just node diagrams. So what about the general case? In a joint work with Professor Hongzhu Gao, we proved that if we have an n-component link diagram, also we need to assume that this link diagram is connected, then the rank of it is equal to C minus n plus 1. C plus minus n plus 1. So if n is equal to 1, we just recover Ayaka's result. Yes. Okay. Yeah, because Ayaka's result says that the rank of it is equal to C. Okay. So here is a complete answer to Kishimoto's question. If we have 2 link diagrams, of course, we need to assume that the shadow, I mean the projection of these two link diagrams are the same. And under this assumption, they are related by a sequence of region crossing changes if and only if for each I, the linking number between I and other components, they have the same parity. Yes. So for each I, they need to satisfy this condition. And in particular, region crossing change is an annotative operation on a diagram of a link diagram if and only if this link is proper. By proper, we mean that for each component, the linking number between it and other components is an even number. Of course, it also follows that actually the result does not depend on the choice of link diagrams. Okay, so this is the answer to Kishimoto's question. Next, I would like to discuss some recent results about the region crossing change on a higher genus surface. First is warning. From now on, we will make a little modification on the definition of region crossing change. Assume we have an orientable closed surface with genus G, and L is a link diagram on this surface. And we choose a region R, and if for a crossing point C, if R appears K times along this crossing point, then we will, by region crossing change on this region, we will switch the crossing point C K times. So for example, in this very simple diagram, because if we consider this crossing point C, because the region R, I mean the unbounded region, appears 2 times along this crossing point. First time, 2, 1, 2. So we will, by take region crossing change on this region R, we will switch this crossing point 2 times, which means that it is preserved. But in the original definition of Ayaka's region crossing change, because it is on the boundary of this region, it will be switched. This is the Ayaka's definition. I have to say, the reason why we change the definition a little bit is because we don't know how to handle the original definition. So it is too difficult for us. So we just make a little modification on the definition. So under this new definition, we can also define an incidence matrix for each link diagram on a surface. For example, here we have this is a torus. Of course, we need to glue this line with this line and this line with this line. So this is a torus, and we have 2 regions here, R1 and R2, and we have only one crossing point here, say C. So now we will have a 2x1 matrix, and because R1, R2 both appears 2 times along this crossing point, so you will get a matrix like this. For the second example, this is a 2 torus, and we have only one region here because this just one. Actually, they are the same region, and we have only one crossing point here, C. So this region appears 4 times along this crossing point, so we'll get a 0 matrix. Also, the number of non-equivalent link diagrams is equal to C to the power of 2 to the power of C minus the rank of this incidence matrix. So we need to calculate C minus the rank of this matrix. However, it is not easy to calculate it. Instead, we find that recall that this matrix has the form R cross C. We found that we don't know how to calculate the difference between C and the rank, but we found that the difference is between R and the rank. R denotes the number of the regions. The integer R minus the rank of the incidence matrix is a homotopy invariant. It means that you can apply some homotopy to a link diagram, and this integer will be preserved. So it follows immediately that for some very simple case, for example, for the two-sphere, we don't let any node diagram is homotopy equivalent to a trivial circle on a two-sphere. So in this case, we can also show that each crossing point is region crossing change, of course, under our new definition. And hence, it is also an annotating operation. Actually, this is not a new result. I think you can you even can get this result from the Alexander's first paper and the definition of the Alexander polynomial. You just need to replace the symbol t with maybe -1 in the matrix defined by Alexander. You can find almost the same matrix here. And so the difficult point in IX proof is you need to handle the so-called negative crossing point. Under this definition, the result is quite easy. So this is the two-sphere case. And for Taurus case, we can also calculate the rank of the matrix, which depends on the greatest common divisor of P and Q is even or odd. And because we know that on the Taurus, we can use some homotopy to transform a node diagram into a standard form. For example, this is the I can say T12.8. Actually, this is a node diagram, but the homology class can be written as 12m plus 8l. M is the meridian, L denotes the longitude. So for the two-sphere and the Taurus, it is easy to calculate the rank of the incidence matrix. But for higher genus, even the homotopy class of node diagram is very difficult. So the general case, the answer is if we use R to denote the standard generator of the first homology group of the surface, and let L be a link diagram, and we can write each component as a linear combination in this form, and here Bij denotes the coefficient. And now we choose all this Bij, and now we can form a new matrix N, which has the size of N cross 2 times G. With this new matrix, we need two lemmas here, but I don't want to explain it. So let's just skip it. The main result is this is a joint work with some undergraduate students in our department, and we show that for an orientable closed surface with genus G and L is an unconvoluted link diagram, the difference between R and the rank is equal to N plus 1 minus the rank of this matrix N. So in particular, for if G is equal to 0, so in this case, the rank N is equal to 0 because there is no homology here. So we can the result can be recovered because rank MH is equal to R minus N minus 1. Yeah, or you can say it is because R is equal to C plus 2. So it's equal to C minus N plus 1. Okay. So this is the result on the higher genus surface. I guess I have 10 minutes. So in the last 10 minutes, I would like to, okay, oh, sorry. Here we have some remarks here. The problem of region cross change on higher genus surface, I think it was first considered by Dasbach and Russo in 2018. But they have some assumptions on the link diagram. For example, they need that the link projection of the link projection is cellularly embedded. It means that each region is homotopy to a disk. And they also need to assume that the link diagram means checkerboard fashion coloring. But our result does not need these assumptions. And in their work, they also calculated the number of non-equivalent link diagrams, and their result can be written in this form: 2 to the power of 2g plus b. Here, b is the dimension of the color of a map. But I don't want to go to details of the definition of this phi. But actually, these two results just gave you the same information. Yeah. Okay. So this is the last game. I would like to discuss the case where 1 appears 3 times in each column of the incidence matrix. In the last game, why 1 appears 4 times in each column is because locally we have 4 regions around crossing points. So because each law diagram or link diagram can be regarded as a planar 4-valent graph. So in this case, we just consider planar 3-valent graphs. Let G be a planar 3-valent graph on the 2-sphere and without bridges. So it means that this kind of edge it does not exist. Yeah. The reason is we want the dual graph of it is provides a triangulation of the 2-sphere. So we assume that it has no bridge. And by state of it, just as before, we just use 0 and 1 and assign to each vertex. And region crossing change means that we switch all the vertices lying on the boundary of this region. And the 2 states are equivalent if they are related by some region crossing changes. For example, this is a complete graph K4. And here we have 0, 0, 1, 1 on these vertices. If we take the region crossing change on this region, then 1, 0, 0 will be switched to 0, 1, 1. So we'll get a new state. So the question is, how many non-equivalent states does G have for a given planar 3-valent graph? This is the answer. Assume we have a planar 3-valent graph of order n, and n we assume that it is greater than 4. If n is equal to 3, the case is quite easy because now in this case we just have when n is equal to n can be n can be, for example, 2, we will have a zeta graph, but this case is very easy. So we just assume that n is greater than 4, and the number of regions is m. And so the result is the number of non-equivalent states of G. If all the regions are even, the result has this form. And if there exist some other regions, but none of them are adjacent to each other, and we also need another condition. So we need this condition. So what is G here? G is the fundamental group of the complement of the odd regions. And H is a subgroup of the symmetry group of order 3. It contains the E and the element which switch 1 and 3. This is a subgroup of the symmetry group of degree 3. I have 5 minutes, so I will give you a very sketch proof on why we need to consider the a region is even or odd. And let me tell you, what is the definition of even is even? It means that, for example, if a region is even, it means that the number of edges of it is even, because this is even, and this is the other region. Yeah. So how to prove this? Again, first we need to translate the question into a question of a hypergraph, and we can construct a hypergraph as follows. The vertex of this hypergraph is just the same as the vertex set of the planar graph G, and each region corresponds to a hyper edge. If this vertex is on the boundary of the region, so the corresponding hyper edge has a form like this. And also the answer is the number of non-equivalent states is equal to 2 to the power of n minus the rank of the incidence matrix of this hypergraph. So we need to calculate the rank of this matrix. This is an example, just like before here. Each row corresponds to R1, R2, R3, and R4. And each column corresponds to V1, V2, V3, and V4. Okay. In order to answer this question, we need to consider a J3 coloring. So what does it mean? If we consider the dual graph of this graph G, we use G prime to denote the dual graph, and this is nothing but a triangulation of the two sphere. And if we choose a triangle, for example, this is a triangle, and we use 1, 2, 3 to color the vertices of it. For example, 1, 2, 3, and we can extend this coloring to some other adjacent triangles. For example, if this is another triangle and the condition is adjacent vertices will receive distinct colors. So because this vertex is adjacent to this one, so it has to be colored by 2. And then you will have this 1, 3. And so you can extend this coloring to some other triangles. But the key point here is, for example, if you want to begin with this triangle and extend it to this one, you have 2 choices. You can use this approach, or you can use this approach. The key point here is, if this vertex point is even, then this coloring extending is well defined. But if it's odd, you will meet some problem. So this observation tells us that we can, if we fix a coloring of a triangle and a sequence of adjacent triangles which begin and ends at the same one. For example, this is the first one, and we can find a loop. And go back. So a loop will give you a recoloring. if there is no arc crossing point here, so this recurring is just the curring of the original curring. But if we have some arc crossing, we have some other vertex here, you maybe will get a new curring. So this will give you a group homomorphism from the fundamental group of the complement of the other vertices to the symmetric group of degree 3. So this is the definition of the group homomorphism phi. And from a global J3 curring, we can get a global J2 curring by replacing 1 and 3 by 1 and 2 by 0. And so what is the relation between this J2 curring with our question? The question is, a global J2 curring will give you a solution to this function. And now this kind of J2 curring will tell you how to calculate the rank of this matrix. Okay, this is the last remark. A very interesting case is it is an odd result that if a triangulation of the two spheres admits only two odd vertices, then they cannot be adjacent. For example, yes, this is a very simple triangulation of the two spheres, and this is other vertex. This is other vertex, and all others are even. So in this case, you find that these two other vertices cannot be adjacent. They cannot be connected by an edge. And this result was first proved by Fix under the assumption of the four-color theorem. And in 1978, and we all know that during almost the same time, Appel and Haken proved the repeated four-color conjecture. But recently, Izmestiev, he reproved this result, but without using the four-color theorem. But as a corollary, we can show that if a triangulation of the two spheres admits only two other vertices, actually they must be compatible. So what is the meaning of the compatible? It means that assume this is an other vertex and this is another other vertex. Choose a triangle here, and we can use the curring 2, for example, 2, 1, 3. And now we can choose a path from this other vertex to this one. And by compatible means that this path will induce a curring to this triangle, and this other vertex must be colored by 2. It means that they are compatible. Otherwise, they are not compatible. So this is a little stronger than the result, because if these two other if these two odd vertices are adjacent, it means that they must be in the same triangle. So if this is 2, this must be 1, 3 or 3, 1. So they can't be compatible. So our result just can be regarded as a little enhancement of the result by them. So I'm sorry. Let's work. Thank you.
Okay, thank you very much. So there is a question or comment? Yeah, your survey is a very detailed region crossing change for every version you state.
Actually,
very nice.
I just want to study the region crossing change problem on general planar graphs, but I don't know how to deal with this general case, so I have to add some restrictions. So we just consider 3 variant graphs. Yeah. But I think there should be an answer for the general case.
Thank you very much for your nice talk. Other questions there is? Okay, thank you very much.
Thank you. Okay.
Next talk will begin with just 1200. Okay. Okay, so the next speaker is Professor Tatiana Kozlovskaya. The title is Group of Chamomile Type and the Singular Braid Group. Please start.
Thank you. Can you see my slide?
Yes.
Okay. Thank you for coming to my talk. I want to tell you about recent work, groups of chamomile type and the singular braid group. The result obtained in a joint work with Valery Georgievich Bardakov. We will give basic definitions of braid group, pure braid group, and singular braid monoid. Also, we recall some well-known facts about presentation of the braid group. We will introduce groups of chamomile type and prove that the singular pure braid group is a group of chamomile type. Note that any n braid can be formed by a finite number of elementary braids, sigma 1, sigma 2, and so on, sigma n minus 1, where sigma I corresponds the geometric n braid formed by crossing the i's strand under the I plus 1 strand, as depicted in the figure. That is, if one considers the braid sigma I and sigma I to the power of minus 1, as in figure, it's clear that they are the inverse of each other. The set of all n braid generate a group. The unit element of this group is a braid represented by all vertical parallel strands. Artin introduced the braid group in 1925 and gave a presentation for this group in 1947. The braid group Bn on n strands can be defined as a group generated by sigma 1, sigma 2, and so on, sigma n minus 1 with the defining relations. The relations sigma I, sigma g equals sigma g, sigma I is called Fa commutativity. Their geometric interpretation are given on slide. There exists a homomorphism of the braid group into the symmetric group on n lattice. This homomorphism maps sigma I to the transposition I plus 1. The kernel of this homomorphism is called the pure braid group and denoted by Pn. In a pure braid group, the beginning and the end of each strand are in the same position. The pure braid group is generated by elements AIG. These generators can be expressed by the generators of the braid group as following. The generators, the braid group, act on the generators AIG belong to the pure braid group by the rules. Denoted by UI, a subgroup of the pure braid group Pn. It's known that UI is a free group of rank I minus 1. The pure braid group is defined by the following relations. The pure braid group Pn is the semi-direct product of the normal subgroup Un and the pure braid group on n minus 1 strands. Similarly, Pn minus 1 is a semi-direct product of the free group Un minus 1 and Pn minus 2, and so on. Therefore, Pn is decomposable into the following semi-direct product of free groups. Let Fn be the free group of rank n with a set of generators x1, x2, and so on, xn. Assume further that out Fn is the automorphism group of Fn. The Artin braid groups Bn can be represented as a subgroup of out Fn. This representation due to Artin himself is defined associating to any generators sigma I of the braid group, the following automorphism of Fn. Here and onward, we point out only non-trivial trivial actions of generators, assuming that other generators are fixed. One of the most interesting problems in the theory of braids is the question of whether Bn is linear, whether it admits a faithful representation into a group of matrices over a field. Homomorphism from group G to the general linear group GLN over a field P is called linear representation of the group G. This question has its origin in a number of interpreted facts, and first of all, the discovery by Burao. Consider the braid group and try to represent it by matrices n by n. More precisely, one takes sigma I to some block diagonal matrix with 1, 2 by 2 block line in 2 rows I plus 1 and 2 columns I plus 1, and all the other 1 by 1 unit submatrix line on the diagonal. The representation where the block matrix looks like 1 minus t 0 is called the Burao representation of the braid group. It was proposed by Burao. The faithfulness of this representation has been an open problem for a long time. John Bierman proved that it was faithful for the case of 3 strands. It was established by Moody in 1991. This representation is not faithful for n is greater than or equal to 9. Later, it was shown to be unfaithful for n is greater than or equal to 5. Long and Payton extended Moody argument to n is greater or equal to 6. Recently, Bigelow proved that this representation is not faithful for n is equal to 5. Thus, the question of the linearity of the braid group remained open. The notion of singular braids was introduced independently by John Byers and John Bierman. The Byers-Bierman monoid is generated by 3 elements, sigma I minus 1, and tau I, and the defining relation. The singular braid group was introduced by Fenn, Kamen, and Rourke. They proved that the Bierman monoid SBN is embedded into the group SGN, which is called the singular braid group. The singular braid group, the singular braid monoid is generated by the unit by classical elementary braid sigma I with the inverse. The generators tau I have a geometric interpretation where the i's and i's plus 1 strengths intersect. Let us define the map of the singular braid group onto the symmetric group. Onto the symmetric group on n symbols by actions of following generators. The kernel of this map is called singular pure braid group. These are interesting questions, and we want answer to them. The first, find a finite set of generators and defining relation for the singular pure braid group on n strands. The second, is it true that the center of the singular braid group on n strands is a direct factor in SPN? Third, construct a faithful representation of singular braid group into the automorphism group of subgroup, some group H, where H is a good group. And the fourth, construct a faithful linear representation of singular pure braid group to the linear group over a field. Let's ask to find the representation of singular pure braid group. We will use the Rademacher-Schreier method to find defining relations of singular pure braid group. We define a rewriting process. It allows us to rewrite a word which is written in the generators of the singular braid group and present an element in the singular pure braid group as a word in the generators of the singular pure braid group. Consider the case when n equals 2. The singular braid group is defined via the following representation. The singular braid group SG2 is generated by two elements, sigma 1 tau I, and is defined by the following relation. Sigma 1 tau 1 equals tau 1 sigma 1. We see that SP2 is generated by three elements, S1 tau 1, S sigma 1 sigma 1, and sigma 1 tau 1. The element A12 equals sigma 1 2 is a generator of the pure braid group P2. The singular pure braid group on two strands is generated by two elements which commutative. Hence, group is a free abelian group of rank 2, where A12 equals sigma I2 and B12 equals sigma 1 tau 1. The singular pure braid group on two strands is normal in the singular braid group on two strands, and the action of the singular braid group on two strands on SP2 is defined by formula. The group sp3 has the following representation. The singular purebred group sp3 is generated by 6 elements, and it's defined by 8 relations. The singular purebred group on 3 strands is generated by elements A12, A13, A23, and B12, B13, B23. The geometric interpretation are given in figure. A geometric interpretation of the first relation of the singular purebred group on 3 strings is provided. We note first that this relation is a relation of the purebred group on 3 strings. The geometric interpretation of this relation given on slide. This relation is a relation of the singular purebred group on 2 strings. The proposition gives conjugation formulas of generators A12, A13, and A23, and analogy for B by generators of the singular braid group. The following theorem describes a structure of the singular purebred group on 3 strings. The singular purebred group on 3 strings is isomorphic to the semi-direct product of some group V with tilde and infinite cyclic group. The group V3 with tilde is an HNN extension of the free product of 2 abelian groups of rank 2. Let's now turn to a question. Is it true that the center of the singular braid group on 3 strings is a direct factor in sp3? We proved that it's true. sp3 is the direct product of center and some subgroup V3 with tilde. The singular purebred group SPN has the following presentation. The singular purebred group SPN is generated by elements A, Ig, Big, and is defined by 14 types of relations. On this slide, you can see some of them. Dashbach and Gemain found a set of generators and defining relation for SPN. We obtain another presentation for it. We proved that the center of the singular braid group on n strands is a direct factor in SPN. But the center of the singular braid group on n strings is not a direct factor, is in SGN. You can see the definition of local representation on the slide. A local representation is called homogeneous if R1 equals R2 and so on equals Rn minus 1. We proved that any linear local homogeneous representation of the singular braid group into the linear group over a field F that is an extension of the Burau representation of the braid group can be defined on the generators sigma I and tau I. In this work, we introduce groups of chamomile type and prove that the singular purebred group, SPN, n is greater or equal to 5, is a group of chamomile type. It means that some properties of SPN is greater, n is greater or equal to 5 can be deduced from property of SP4. It's in particular, one can find a presentation of the singular braid group by presentation of SP4. Similarly, a result is true for some braid like groups. Suppose that a group G is defined by a set of generators X and a set of relation R. In this case, we say that G has a presentation. We will denote the set of generators X and set of relation R as on the slide. First, we give the definition of group of chamomile type. Let G be a group. H is its normal subgroup. G bar is a set of coset representative H in G. The subgroup H is said to be a subgroup of chamomile type with highlighter petal H0 and conjugation set M. If H0 is a subgroup H, M is a subset of G bar that contains a unit element of G, and the following equality holds. We proved that the pure singular braid group SPN n is the greater or equal to 5 is a group of chamomile type. The structure of the pure singular braid group on 5 strengths we give as example. The group SP5 is a group of chamomile type with highlighter petal SP4 and conjugation set sigma 4, sigma -1, sigma 3 -1, sigma 4 -1, and so on. Thank you.
There is a question or comment. Okay, so one question is singular braid is some geometric meaning. Do you know some geometric meaning of singular braid? No.
Yeah.
Okay.
Geometric interpretation.
Mm-hmm.
You.
Yeah. Something. Where come from singular braid?
Is it the same? Is it the same as what you would get if you used rigid vertex graph embeddings and made braids out of them? Is that the same as the singular braids? I didn't check the definition. You know, the rigid vertex graph embeddings are quite natural. And you can make a singular braid group associated with them, but I'm not sure that's the same as this one. We have to look.
Yes, here you can see the rigid vertexes. You introduced two definitions of the graph. In this case, you can see the rigid version.
Mhm.
And also, I would like to say on the question of Professor Kawauchi, the singular braid were introduced in the paper of Bierman for studying of finite type invariants.
Yes.
Vasiliev introduced finite type invariant, and for interpretation with invariant, Bierman introduced singular braid. Singular
Okay,
braid.
thank you. Mhm. Okay, there is a other question or comment? Okay, thank you very much.
Okay,
Thank you. I have a small announcement. According to the schedule of talks, we have some changes for tomorrow and the day after tomorrow. Let me show you, let me demonstrate you the schedule. Right? Do you see? So we decided to interchange the talk by Mahendra Singh and the talk by Krishnandu Gangapadhyay. So we will make this interchanging. So that's it.
Anything else? Nothing else. Uh-huh.
Nothing else.
Okay, thank you. Next talk with just 1600, yeah? Next talk. Okay, thank you very much.
Right, right. The next session will start after the lunch break, very long indeed, at 16, yes, by GMT +7 time zone. It's 16 o'clock. So see you after the lunch.
Okay, see you.
Thank you. I'm glad to have been able to overlap a few hours with you.
Goodbye.
Bye.
Hey, everyone.